There can be three types of graphs. A graph can be Eulerian, it can be semi-Eulerian, or it can be non-Eulerian. In Eulerian graph, every vertex has even number of arcs connected to it. In a semi-Eulerian graph, exactly two of the vertices are odd and every other vertices are even. In non-Eulerian graph, more than two of the vertices have a valency of odd. Two concepts must be very clear. When we have a weighted graph, it means that the lines connecting the points, that is, the arcs connecting the vertices, have a value, and that value is called the weight of the arc. AB has a weight 11, and the arc AE has a weight 10, and the arc BE has a weight 7. The valency of a vertex is the number of arcs connected to it. At the point A, two lines are connected to it, so it has a valency of 2, which is even. At B, two lines are connected to it, so it has a valency of 2, which is also even. It can be thought of as the number of roads coming out of a city is the valency of that city, and the length of each road is the weight. The purpose of route inspection algorithm is to find the shortest path as a graph is traversed. If it's an Eulerian graph like we have in this diagram, we don't have to think about the shortest path because there is no extra path to be added for it to be traversable. All we have to do is take each value and add it up, so it would be 11 plus 10 plus 7 plus 9 plus 8 plus 12, which turns out to be 57. This graph is semi-Eulerian. Now we have to add two of the arcs so that we can make it Eulerian. So the first step of route inspection algorithm is to make sure the graph is Eulerian. So first let's check which two vertices are not even. So we see that there are two vertices that has odd valency, so it is semi-Eulerian. The task is to make this semi-Eulerian Eulerian. In order to do that, we need one arc for Q and one arc for T. So if we connect Q and T, so like this, if we connect Q and T, so then Q now has 4 arcs and T also has 4 arcs, so now they're even. So if we connect Q and T, the entire graph becomes Eulerian. So this is the connection. Now we have to see how many ways can we go from Q to T. We have to take the smallest value, the shortest traversable route from Q to T. So let's check. If we take QT, the most basic would be Q to S and S to T. So Q to S and S to T, that turns out to be 4 plus 5. So this is 4 and 5, so this is 9. Another option would be if we take Q to R and R to T. In that case, it would be Q to R and R to T, so that would be 7 plus 8, which is 15. So 9 is still the smallest. Then we have other options. We can go Q to P, P to S, S to U, U to T. In that case, it would be 6 plus 2 8, 8 plus 3 11, 11 plus 2 13. So it's much higher than 9. So it turns out QT, if you want to go from Q to T, the shortest path is going to be Q to S and then S to T, which is 9. So 9 is the shortest route that can be added. So we need to know, before QT was added, what was the total weight of this graph. 6 plus 2 plus 5 plus 3 plus 4 plus 2 plus 8 plus 7, it turns out to be 37. The shortest path would be, so the length would be total length plus the shortest length of QT for making it Eulerian, that is 9. So this is going to be 46. If we start from S, one traversable route would be S, Q, P, S, U, T, Q, R, T, S. In this problem, we have to solve the route inspection problem starting and finishing at A, which basically means we have to find the shortest route. The first thing to do would be to check whether it's traversable or not. In order to be traversable, it has to be Eulerian. So we have to check whether this is Eulerian or not. If it's not Eulerian, we have to add arcs and make it Eulerian. It turns out that 4 of the vertices are odd and only one vertex, which is E, is even. That means there are a number of possibilities to connect the two vertices. So one way to do that is we can connect A with B so that both A and B would now have 4 arcs. That means they would be even. And then we can connect C with D. So one connection would be AB and CD. Another option would be we can connect A with C. In that case, it would be B with D. So it can be AC and BD. And another option would be we can connect A with D and we can connect B with C. So it would be AD and BC. So there are 3 possible connections of the vertices to make it Eulerian. Now let's see which has the shortest route. So if you want to go from A to B, so from A to B, it's 8. We can also have, in order to go to A to B, we can also have 5 plus 6, which is 11, so that is larger, so 8 is the smallest, so we have 8. For going C to D, what we have here, we have 9. If we go for C to D, if we go 7 plus 4, that is 11. If we go 6 plus, that is larger, so C to D is 9. So that turns out to be 17. Now the other option is connecting AC and BD. So if we connect A and C, so A and C is 5 plus 7, 12. We can also connect A and C by this. 7 plus 9 is 16. 8 plus 6 is 14. So 7 plus 5 is 12. So this is the smallest. So we can write this 12 plus BD. In order to connect B and D, 6 plus 4 is 10. We can also connect B and D through BC and CD. 6 plus 9 is 15. 6 plus 4, 10 is the smallest. That turns out to be 22. So far, ABCD, this is the smallest, 17. Now let's connect AD and BC. So we have AD, so AD is 7. If we add 5 plus 4, that is 9. If we go through, so 7 is the smallest, so this is 7. Plus BC, so BC is 6. If we go to B to C, traverse from B to E and then E to C, it is 6 plus 7, 13. So B to C, 6 is the smallest, so this is 6. So it turns out to be 13. So this is the least value. So we are going to add AD and BC to the weighted graph. So AD, so let's connect this, and it is going to have a weight of 7. And then we can connect BC and it's going to have a weight of 6. So now to solve the route inspection problem, we have to add to the total weight of the graph the shortest path that we just found. So the total weight should be 7 plus 8 plus 5 plus 6 plus 6 plus 7 plus 4 plus 9, and this is 52. So the length is going to be 52 plus the 2 arcs we added. The shortest arcs is going to be 13, and this turns out to be 65. So the traversable path from A to A would be A, B, C, E, B, C, D, E, A, D, and then back to A.